In this virtual lab, we are going to study oscillating physical mechanisms. First, we are going to see a vertical spring with a mass attached to its end. This lab will set the stage for a more mathematical implementation of the only physical law that we have actually learned in this course, the Newton's law of motion. In this video, we will combine theory, observation, and a bit of our intuition. First, we are going to study the physics of a vertically oscillating spring, of course by applying Newton's law of motion. The next step will be to observe the spring oscillate with a force sensor and a position sensor, and use these numbers to see whether theory agrees with experimentation. Let's take a first look at the natural length of our spring. For the record, the spring is attached to a Pasco force sensor, which will be one of the two instruments that we are going to use in order to collect our data. Now let's hang our 100 grams mass from the spring. The spring now stretches to a new length. The difference between the natural length and this new length will be called delta L. This is the so-called equilibrium point. The equation displayed here, mg, in that is the weight, equals to k, the spring constant, times delta L, provides essential clues for the rest of this experiment. Now let us give our spring a small displacement and let it oscillate around this equilibrium point, shown here with a purple dashed line. At any given point, there are two forces acting: the spring pulling up and the weight pulling down. These are essentially the forces for which we will write Newton's law of motion, sigma of F equals mass times acceleration. We will need to do some basic algebraic manipulation, but nothing too terrible. Substituting these two forces, but also acknowledging that mg equals to k times delta L, which we pretty much found from the equilibrium point, we notice that the term mg cancels out from the left and right of the equation. Well, that leaves us with k times y, which is the displacement, plus mass times acceleration equals to 0. If we further substitute acceleration with essentially what it is, that is the second derivative of the displacement with respect to time, then we get a very important equation. This equation describes what we call a simple harmonic motion. As a matter of fact, any equation that encompasses acceleration plus a constant times the displacement equals to 0 always describes a simple harmonic motion. But what makes this equation uniquely tied to our oscillating spring is this constant that is highlighted. That is the spring constant divided by the mass of the oscillating object. We will see how this constant plays an intricate part in the solution of this equation. This equation is also known as an ordinary differential equation. It is okay if we never had ODEs before. What is important here is that this equation is a solution, that is, displacement as a function of time, the displacement is indicated with a y, equals to the maximum displacement, indicated with capital A, times the cosine of what we call the characteristic angular frequency of this oscillation, denoted as omega, times, of course, time. The most important parameter in this equation is this omega. It is equal to the square root of the spring constant divided by the oscillating mass of our object, which, if you recognize from before, it is the constant from our simple harmonic equation. It is very important to know that omega does not depend on anything else other than these two variables. The units for omega are radians per second, which means that when you compute the cosine term on your calculator, you must have it in the radians mode. Finally, the maximum displacement A is measured in meters. Since we now know the frequency, what we call the characteristic frequency of the spring's oscillation, we can further infer the oscillation's period, which essentially tells you how long it takes the spring to complete one full oscillation. The units for the period capital T are seconds. Now let us try to understand a bit better how these variables omega and period affect our oscillation. This is a numerical simulation from Mathematica that is also made available to you in your lab manual. On the upper right panel, we see the displacement of the spring with respect to time. This is the cosine function that we discussed earlier. In the lower panel, you see the velocity of the pendulum, a sine function, since the velocity, of course, is the derivative of the displacement. If we now increase or decrease the mass of the hanging object, you'll see that the period will also be affected. For example, increasing the mass increases the period, and therefore you have a longer oscillation, and vice versa. Increasing the stiffness of the spring has the opposite effect, in that the oscillating becomes shorter in time. There's one other very interesting effect. We call this the damping factor, and essentially is a quantification of the friction, since in real life we always have friction. The higher the damping factor, the faster the amplitude of the oscillation goes to zero, as you can see from this plot. As we further increase the damping factor, we end up with a process that does not even oscillate. Well, you can think of a revolving door. When you give it a push, it will rotate, say, a couple of times until it stops. However, if the damping factor of this revolving door is very high, then the door will not even make one full oscillation until it comes to a full stop. Now it's time to get ready and collect some real data. We give our spring a small displacement downwards and gently let go. The spring starts to oscillate, as you see in this slow motion video. Right now we are collecting data with a position center at the bottom that in fact works as a sonar, but also with a force sensor on top. This panel represents the real-time data acquisition. The upper panel represents time on the x-axis and displacement on the y-axis. The lower panel represents time and velocity. We can gather very important information from these plots. For instance, the maximum velocity, the period of the oscillation, the velocity of the spring as it goes through the equilibrium point, etc. The upper panel also informs you about the maximum displacement, annotated as capital A. This information is essential when answering the questions in your lab reports. You will be provided, of course, with the actual data on an Excel spreadsheet, and you will find the link to this spreadsheet in your lab manual.